All right, let's take a look at some physical properties of some gases. And for these physical properties, a lot of gases behave the same under normal conditions. And we call these ideal gases. So ideal gases behave exactly like you would expect them according to the kinetic molecular theory. And most gases will behave as ideal gases under quote unquote normal conditions. We'll explore what that means a little bit later. But let's just go take a look at some of these properties. So we have volume. The volume of a gas is going to be proportional or inversely proportional to pressure. So this little symbol right here means proportional. And you can see this is 1 over P. So whenever you have 1 over X, you're inversely proportional. And what that means is that these two are going to do the opposite of one another. So what I mean by that, as volume increases, right, little up arrow means that volume is increasing, our pressure is going to decrease. And that makes sense. Remember, pressure is force over area. As your volume goes up, your area goes down. And so your force or your pressure is going to go down. Right? As one goes up, the other goes down. Volume goes up, pressure goes down. As pressure goes up, volume goes down, vice versa. Right, so this one makes a lot of sense. This is also what's known as Boyle's law. The next one we have is that volume is proportional to temperature. This is what's known as Charles' law. So as one increases or decreases, so does the other. So as one goes up or goes down, so does the other. Assuming everything else is kept constant. So for example, if you put a balloon in the freezer, you're going to see that balloon is going to deflate because as you put it in the freezer, the temperature goes down, so the volume is going to go down. And then once you take it out of the freezer and let it warm back up, it's going to expand again. A popular kind of thing here is if you watch football, at one point the Patriots were accused of cheating because they deflated footballs. But what the league didn't take into account was that it's cold outside. So, they inflated the balls inside where it was warm. They took them outside where it was cold. The pressure or the volume went down, or the pressure went down, but it's proportional to the volume. And so they accused them of cheating when really it's just an application of the ideal gas law. And then finally, we have one more. Volume is proportional to N. And N is our moles of gas. Right, or the amount that we have, right? And that makes sense. As you blow into a balloon, you're adding more gas to it, and what you're seeing is the volume increasing, right? And so that's what's known as Avogadro's law, right? Same guy who found out, the number for the mole. And so what we can do is we can combine all of these laws into one equation that'll let us figure out a lot about gases. And that equation is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, right? Nothing too bad there. Let's take a look at these subscripts, what these subscripts mean. So what the ones mean is under your variables, under conditions 1. And then these would be your variables under conditions 2, right? So if you know some of these variables and then you put them under different conditions, then you're going to be able to see them change and you're going to calculate exactly how much they can change. One important note is about temperature here. Here we're dealing with absolute temperature, right? Not a difference in temperature. So that means that we have to use Kelvin, always have to use Kelvin. And then another thing you're going to see with problems like these is they won't always include all 4 variables. For example, they might only deal with pressure and temperature or, number of moles and volume, that kind of thing. So if only given some variables, we're going to assume the others stay constant and cancel out. Right, so if you're not given any information about those variables, essentially just ignore them. So let's take a look at an example problem. What is the volume of 10.0 liters of gas when the pressure is increased from 1.00 atmospheres to 2.00 atmospheres, right? So we have our equation P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so what we're given first is the volume of 10 liters. So we'll put that in as V1. And then the pressure is increased from 1 atmosphere. So that means under conditions 1, we have 1 atmosphere to 2 atmospheres, right? So that's under conditions 2. So we'll plug that into 2. Note we did not mention the temperature nor the amount of gas. So we're going to assume that stays constant. And so we're just going to go ahead and cancel them out. And you can rewrite, if you'd like, your equation as P1 V1 equals P2 V2. And then what we want to solve for is our V2. So V2 is going to equal to P1 V1 over P2. And then we simply plug in our numbers. So for pressure 1, we had 1 atmosphere. For volume 1, we had 10 liters. And then for pressure 2, we had 2 atmospheres. Notice that it doesn't matter what units you use for any of these variables, but they have to match. So for example, here we used atmospheres for pressure, so they both have to be in atmospheres. They could both be in torrs, they could both be in millimeters of mercury, that kind of thing, but they have to match with one another, right? If one is atmospheres, the other has to be atmospheres. The only exception to this is temperature, and temperature must always be in Kelvin. You cannot use Celsius at all in these problems. If you're given Celsius, convert to Kelvin. Anyways, atmospheres and atmospheres will cancel out. So you can see the unit that we'll be left with is liters. And in this case, we do the math, 5.00 liters. Right, and that makes sense. We said pressure and volume were inversely proportional. So as one goes up, the other goes down. And when we went from 1 atmosphere to 2 atmospheres, we doubled the pressure. So it makes sense that our volume is halved. So just do some practice problems. Overall, these problems are just kind of plug and chug type of problems.